Hi, my name is Alana Goldstein, and on behalf of our team, I'd like to welcome you to our video presentation on our return to launch site rocket project named Rocky. This is our senior design project, meaning we've been working on this for the past several months, designing, building, and testing a rocket capable of returning to the launch site after flight. In this picture, you'll see all of our team members, and they will introduce themselves now, starting from left to right, as shown in the picture.
Hello, my name is Price Newsom.
Hi, my name is Emma Moore.
Hello, my name is Josiah Concepcion.
Hello, my name is Diego Lopez.
And hi, my name is Alana Goldstein again. So now for a quick introduction into the RTLS Rocket Challenge, as well as the design concept that our team chose. Our mission was to develop a reusable rocket system capable of precision landing on a designated launch platform. The rocket aims to achieve or exceed an altitude of 2,200 feet, incorporate a guided recovery system for safe and controlled descent to a designated target, in our case, the actual launch pad, and enable data monitoring through sensors and video recording. The design concept that our team chose would be one that mimics the descent or controlled descent of a skydiver.
So here's the first picture of our engineering approach. This is our open rocket design that we created using open rocket software. This was the team's 7th iteration of this airframe, and the main accomplishment of it was ensuring that the subsystems were integrated into the airframe and had enough room and space for packing to be completed properly. As each component was designed separately, the airframe design needed to be able to fit all components in a secure manner while also ensuring that the weight remained low and the stability margin was within the acceptable limit, while also maintaining the projected minimum apogee requirement of 2,200 feet. The rocket itself measured to be about approximately 59 inches in length with a 5.5-inch diameter. In this photo, you can see the final integration of all subsystems as they were assembled in the rocket body. The first thing that you can see is the nose cone, which includes a bulkhead and clay ballast sitting on the top of the rocket body. You're also able to see the parachute attached to the electronics bay and the shock cord, all sitting on top of the motor mounting system. This system was comprised of a motor tube and 4 centering rings, and between the top and middle centering rings are where the fins were through-walled and epoxied to the motor tube to ensure maximum stability.
For the motor selection and integration process, our main objective was to choose a motor capable of reliably reaching our required apogee of over 2,200 feet. After evaluating several options based on total impulse, burn duration, thrust curve, and cost, we selected the Aerotech i600. We specifically chose a 9-class motor because H-class motors simply aren't strong enough to put our rocket at the height that we needed. The motor was installed into the motor mount using these centering rings and tube within the rocket's lower airframe, and it was tightly secured using a hose clamp to ensure that it wouldn't go anywhere and it would remain stable throughout the whole flight path. Despite strong wind conditions during launch, the motor performed as predicted with stable ignition and burn characteristics, ultimately getting us an apogee of 2,380 feet AGL, which exceeded our minimum target.
So here's a brief overview of our engineering approach to the command module. So in order to make this an RTLS rocket, we needed a way to control the parachute for a controlled descent. So here we have, on the left side, we have the beginning prototype or the concept drawing. So here we can see the command module, which contains the servos and a bearing to keep the rocket from tangling itself. And on the right, we have the final CAD model of the electronics bay. And here we have 2 servos, a camera to record the descent, along with a GPS to monitor the location of the rocket and the receiver and batteries that house everything. So in order to control the parachute, we use these 2 servos that act in opposite ways to control the rocket, either left or right, and they go up and down to create more or less lift.
So here we have the parachute design. This is the twin keel Rogallo. We chose this for its simplicity, mostly. And this is the different variations of the parachute. The parachute was made by myself using nylon ripstop and Kevlar for the lines. And then here you can see the finished product.
Here we can see the manufacturing of the airframe, which took place over 2 days. In these photos, you can view our team as the rocket components were assembled one by one. In the first photo, you can see 4 team members holding the rocket tube steady as the fin slots were cut from the blue tube. The second photo shows the centering rings being epoxied to a paper towel tube, which acted as our motor tube. The third photo showcases the first fin that was inserted in epoxy to the motor tube and airframe. And the last photo shows the team inserting the motor mount system into the airframe, which was then epoxied at 3 different points, the top, the middle, and at the very bottom of the assembly. Here are just a few more photos of the manufacturing of the airframe. The first photo is the final assembly of the rocket, where you are able to see the blue tube, the nose cone, and the fins as separate entities of the rocket. The second and third photo show 2 of our team members manufacturing rail guides in the bulkhead, and the very last photo is of the 3D printed nose cone after it was done printing.
So here's a quick demonstration of the electronics in the electronics bay, be it working with the controller and receiver. So in order to make sure the electronics worked in the rocket, we had to set up a prototype, and this was the quick prototype that ensured that the servos fit along with the GPS, and to make sure that the hole placements were correct and that the servos could produce enough torque to actually make the parachute function the way it needed to.
So what you can see here is the testing of the parachute system as a whole. This attempt was a bit of a fail, but we at least tried this 3 times, and it was a success one time where it completely deployed. It went, in the correct direction of the wind. And yeah, we attached a 4-pound weight to the bottom of it, to the electronics bay, in order to simulate the rest of the rocket that we weren't able to use here. Yeah, we dropped this from like a 3-story building, like the stairs here, in one of the engineering buildings to test the system.
Lessons learned. On launch day, the team spent about 2 hours preparing the rocket for launch. This process included attaching the parachute to the electronics, folding the parachute properly, assembling the motor, and packing the rocket body. Once ready to launch, the team headed out to the launch pad where the rocket was guided onto launch rails and was attached to the electronics for the launch pad. And here we have a video of our launch. And while that goes on, I'll speak about some issues we encountered. So as you can see, we are lined up almost at a 90-degree angle. So our rocket shot straight up, and due to some higher than usual speed conditions, our rocket started to drift a little bit. This negatively impacted the flight path and caused the rocket to go in the opposite direction, meaning that our team member down below had to apply more active control so we could actually bring the rocket back to the site.
So here's the flight profile of our rocket. The GPS on board was able to track all 3 axes, so we were able to see a 3-dimensional view of our rocket's ascent. So basically, it took off from the launch position and went practically straight up to 2,380 feet, which was our apogee. And then from there, it fell until the parachute deployed and then caught the wind. So we weren't able to control it as much as we would like to because the wind conditions were on the high side around 9 to 15 miles per hour in the northwest direction. And we had a descent rate of around 17 feet per second. So this resulted in us landing approximately 2,000 feet away from the launch position.
So while the RTLS challenge was an academic project, its impact goes far beyond the classroom. The same return to launch-site principles are being applied in real-world aerospace industries to reduce space debris, lower manufacturing and launch costs, and enable more sustainable and frequent space missions. For us as students, this challenge served as a hands-on introduction to the kind of thinking and problem-solving that's becoming standard in the industry, especially as companies focus more and more on reusability and cost efficiency. It's helped us prepare to enter a workforce where RTLS technologies are not just innovative, but they're essential.
Finally, we have some team reflections. This team was challenged in every way possible, from technological design to budget and time management. However, it did force us to learn how to work together as a team and attack our problems head on. We would like to take a moment to thank our advisor, Dr. Walter Hammond, without whom this project would not have been possible. We'd also like to thank Dr. Kurt Stressall for his imperative input into our design and assisting us during the launch. Finally, we'd like to thank our panelists and the alumni for their time and consideration. Thank you.